Welcome to the second lecture, the second week, this course on machine learning. This lecture will focus on the characteristics of objects, categories, and features. Essentially, the building blocks needed in the area of classification and concept formation. This lecture will discuss the following items. First, we will talk about objects and features, and then we will also discuss something we call the object space and something we call the object language. Furthermore, we will discuss categories, category structures, what we call the category space, and what we call the hypothesis. So the first group of items refers to the way we phrase our data. And the second group of items refers to how we phrase our abstractions. So let's start to talk about objects. And by object, I here refer to the basic data items on which we base our analysis. As you see, there is a very complex jungle of terminology here. People use very many words. Object, I like personally as a term, but I think in many cases data or maybe data item is a good word because it's understood by many people. Some people talk about record, some people about tuple, some people talk about row, some people talk about vector. People from statistics tend to talk about instance or example or training instance or training example. There are also somewhat more exotic terms like thing or entity. But essentially all these terms is supposed to refer to the very concrete data items or data objects on which we base our analysis. So then the question is, how do we characterize an object? And then we come to the use of the word feature. So in the same fashion that there are many words, synonym words for object, there are many synonym words for feature. So I highlighted feature here as I highlighted object, but there are of course alternatives. You can talk about property of an object, you can talk about attribute of an object, characteristic of an object, you can talk about a field, but of course field in a way is compatible with record. You can talk about column, but then that also is somewhat compatible with whether you talk about vector or row and so on. And then we have words which are primarily used in statistics, variable. And for variable, there are various variants of that. We can talk about output variable. We could talk about independent variable. We could talk about predictor variable. We could talk about variants of feature. We could talk about target feature. We could talk about category feature. And of course, there are special semantics here. I mean, a predictor variable and an independent variable are more or less the same thing. That is separate from an output variable, because normally when we talk about output variable, we mean the kind of class label that relates to abstraction we want to create. The same for category feature. So output variable and category feature could be more or less synonymous. unfortunately, I don't think anybody can assume that people will be totally consistent. I must admit, myself, I switch between words. Sometimes it feels right to talk about data item. Sometimes I feel it feels right to talk about object. But as long as one have the basic understanding that there are two kind of phenomena here. On one hand, there are the concrete objects, and there are synonyms for that. And then there are ways of characterizing those objects, and then there are synonyms for that. So finally, one can say that you need a formalism to express these things. It's not something very advanced. It's just a simple conventional formalism in which you express your features, and of course some formalism in how to group features so that they can form objects. But when one refers to this formalism, or this kind of simple language in which objects and features can be expressed, we normally talk about the object language, or the data language, or the observation language. So just a few words about the types of features. There, of course, can be any types, but the common types or normal types that we will see within this course are the following. So first of all are the ordinal. You can call them binary or Boolean. And then we have the numerical, which can either be discrete or continuous. And finally, we have the symbolic features, which are simple symbols, or we can have simple structures. The most common there is, of course, lists, but it could also be more complex, like graphs and so on. So here comes one example from the zoo dataset. One data item picked out happened to be buffalo, and as you can see, the object language here is a very simple one. It's simply a convention for listing the features in a row. And you can see then below that we said already that the features here are mostly ordinal. Only one is discrete. Two features are special because they are not predictor features in the sense that they predict the class, but they are classification features that pre-classify each object. There are like two here because on one hand the task is to classify these animals on a high level. So the class type with values from 1 to 7 is used for that. But then there is also an animal name, which is essentially the name of that specific kind of animal. And because there are no duplicates here, it's of a buffalo or some other animal. It's just the identity of that data item. So let's talk now about object space. So by object space, I mean essentially the space of all possible objects as can be described by the object language. So this, depending on the language, and this can be bigger or larger, but this should be separated from the set of objects that we consider. So this means, with this convention, the data set the set of objects considered for evaluation is just a subset, normally, of the object space. And depending on how the features are set up or chosen, this could be a dense or sparse space, meaning that only the subset is a pretty small subset out of the total object space. But there can be other words here. The sample is a word popular in statistics, which also means the set of objects you actually look at. Training sample, statistical sample. Then one can also use words related to vector or record. We can talk about tables and arrays. So if a data item is a row, a feature is a column, then the data set is the table of all those rows and all those columns, all those rows. And of course, an array is a way of representing a table. Training example set is another word that can be used for this whole subsets of objects that we consider. So let's take a few examples from the zoo dataset. So we look at the object space first of all again. So the object space or population is a set of all potential feature vectors with feature values as can be expressed in the zoo object language. So object space in the way I phrase it here is syntactically defined by the object language. The sample or data set in this case, in this example, is the whole set of zoo feature vectors as described on one of the earlier slides. A word that is a little tricky to use because it's inherited from philosophy is extension, because normally in philosophy, extension of a concept means the set of all entities in the world. So the extension of the concept of Buddha would mean the set of all buffaloes in real life. It's tricky to use because not necessarily we have chosen our representations in such a way so that they truly represent all living creatures of a certain kind. So therefore, I would avoid the word extension. So now we come to what is called the hypothesis space, and actually how the hypothesis is defined from the definition of a category. So actually, if we look at the term category, there are many synonyms, really a lot. So we talk about categories, we talk about concepts, we talk about classes, we talk about hypothesis, we talk about target function, we can talk about type, we can talk about schema, we can talk about model, we can talk about classifier, we can even talk, if we are a little more philosophical, about the intention of a concept. So all these are words to capture the abstraction of the concept. The hypothesis language, the language for expressing the abstraction, can of course theoretically be any language. It could be different from the object language, but in many cases, and very typically, it's syntax-wise consistent with the object language. Of course, there have to be minor, even in the simplest case, there have to be minor additions. So for example, the syntax for feature values have to be extended with Jupyter generalizations, the normal values, because a hypothesis or a concept definition is always an abstraction from a concrete object. So if we have a concrete object expressed in terms of features with concrete values, if we want to formulate that abstraction, we need some wildcards, we need some variables that allow us to generalize the feature values. Normally, we have available background knowledge that also can constrain which kind of abstractions are meaningful. So this constitutes a priori knowledge outside the knowledge that we get out from our objects or from our data. So this background knowledge we can normally be embedded in the hypothesis languages through simple language constraints. And if we embed this knowledge in the language, we normally call this a language bias. It actually is a learning bias because we can only learn what the language allow us to learn. Finally, what is a hypothesis space? So the hypothesis space is then actually the space spanned by what can be expressed in the hypothesis language. Okay, so let's talk a little more about terminology here. So we introduced the word object. We introduced the word category. So we have a definition of a category expressed in a category or hypothesis language. So one way of talking about is that an object is an instance of a category. And of course, a category is a generalization of an object. But then we also have the relations to the object space. So essentially, given a specific category definition, one can look at the subset of the object space consistent with that category definition. So this means that all objects that fulfills the constraints of the category definition. This subspace is normally bigger than the actual subset of the dataset consistent with the category definition, because there may be a lot of objects that is not there at this point, but it's still expressible in the language we created. So of course there is a subset relation between the subset of the dataset and the total subset of the object space consistent with the category definition. And of course an object is a subset, is an element of the subset of the dataset. So this is just a little picture to show you these kinds of relations that exist within this terminological framework we have set up. So you may have found the discussion around the last slide a little abstract. So let's take a very simple example from the zoo dataset. So actually here you find the subset of all fishes taken out from the dataset. Okay. So then the question is, what is a meaningful generalization of all those data items? Yeah, the simplest way of handling this is, of course, first of all, to choose a hypothesis language, which is close to the object language, which I already earlier stated, that is the normal way of going forward here. Apart from following the same structure, what one have to do is, of course, to introduce some generalizations of feature values. As in this case, we only have ordinal values, so we only need some kind of wildcard here, like a question mark. So you can see in red an abstraction, an abstract record, which is in this case is the concept definition, where you find wildcard in the positions where the subset of the dataset include contradictory or complementary values. So going back to the last discussion on terminology, we have a data set, which is the subset, consistent with the concept definition. Then theoretically, of course, we can think about an object space, which is slightly larger because there are typically combinations of the wildcard values not covered by the actual subset of the dataset. But it's not explicitly depicted on this slide. So now we turn into something different. So apart from just looking at objects and categories, we can also look at category structures, which is pretty typical in any domain analysis, which means that we not just have a simple level of one category, but that we characterize objects in our domain in some structure. And such conceptual structures or category structures have also many names. Class structure, class hierarchy, class lattice, concept structure, concept hierarchy, type structure, or taxonomy. And of course, it's possible in machine learning not only to learn one level of categories, but also to learn multiple levels of abstraction, which means it's possible to learn category structures. So apart from persistence and domain relevant category structures that really make sense in the domain, it's of course also possible to work with temporary structures as part of the learning process. And we will come back to that, but there are examples of such things like, for example, version spaces. So obviously, when we add levels here with categories on several levels, of course we can generalize. So we can define specialization and generalizations relations between all these levels. So finally, in this slide and the next slide, I'm just going to illustrate for you how it can look in the general case. So the most common case is one looks at concept hierarchies, which is a tree structure. So we abstract from objects in several ways, levels in a hierarchical way. The other variant of that is what we call a concept lattice, and it's a very similar thing. The only difference here is that in a lattice, it's allowed to have multiple generalizations upwards. This means that you can generalize from category 6 to category 3 or category 2 in parallel. Many times in reality, lattices better maps onto the real situation, but technically, in most cases, hierarchies are more easy to handle. So, to convince you that multiple levels of abstraction, multiple levels of categories or concepts is not a purely theoretical thing, I show you here an extension of the zoo example, where I'm actually just followed one path from one kind of item in our data set, the buffalo. And actually what you see is all the established zoological super and subcategories. And as you can count, there are 13 or 14 levels from buffalo up to animal. And of course, this is a domain where zoologists have worked for hundreds of years with the effort to find the kind of optimal taxonomy for the area. So of course it's not likely in new, more artificial domains that you find this depth. But I want to show it you as one extreme case, and illustrating that many levels of abstraction is not just theoretical thing, but that it occurs in practice. Another observations on this slide, which is mere of a parenthesis, is that if you remember the features that were used in this data set, and then compare to features that you can infer to be important from this kind of categorization, you will see that they are not identical. Not surprisingly so, because actually what's shown on this slide is the line from the buffalo to the top. And of course, if we only want to classify animals on that line, starting from buffalo, going up to animals, then a certain set of features would be optimal. In the general case for our data set, we want not only to classify mammals, we want to classify fishes and insects and so on. So this means that for that general scenario, we need a broader range of features than that set that is optimal only for going down the buffalo line, so to say. So everything here, of course, depends on the purpose. So finally, I want to comment on what happens to features in this kind of more abstract category structure. So of course, when a conceptual structure is formed during a learning process, features will be attributed to the categories of different generality. I mean, in the simplest case, we only have a object of category. It's not an issue. But if we consider many levels, the normal way of looking at this is that every level, in a way, of abstraction contribute to a certain specification of certain features. Also, the common way of looking at it is that when you understand what is the features of an object in a certain subtree of a conceptual hierarchy, one looks at it the way that hierarchies further down the line inherit the same features as categories higher up the line. Also, normally features are not normally spread evenly across the abstractions level. Most features are grouped in the mid-range of the conceptual structure, and this kind of mid-range is termed the basic level. Of course, it all depends what you classify and how you arrange your structures, but anyway, doesn't really matter how you do it, because depending on how you do it, it's possible always to say that some level is basic. And a very simple example you can see here. So if we look at various kinds of fruit trees, in the middle we have trees like apple trees, peach trees, grape trees, and so on. More abstract is fruit trees. More specific are specific kind of apple trees, like Macintosh trees, delicious trees, and so on. And then it turns out that if you think about what kind of characteristics you can attribute to each level, you will normally find that is more natural and more easy to attribute characteristics to what is here termed the basic level. Of course, again, with a disclaimer, that is, the basic level is something relative, and relative to the way you set up the category structure. So we reached the end of this lecture. Thanks again for your attention. The next lecture will be on the topic feature-related issues. Bye and thank you.